it is unreasonable in many circumstances, and one could argue all circumstances, to expect exponential growth to continue indefinitely. Consider a situation like a bacterial culture growing in a dish. At first, we might expect exponential growth as shown by curve A. However, this cannot be expected to occur forever. The dish is only so big, and the nutrients are limited. Curve B might be a more appropriate model. So we get initially rapid growth. We can see how close that is to exponential. But then after a point, as the dish starts to fill and the nutrients start to run out, we're going to get a leveling off. Exponential growth is not a very sustainable situation, since it depends on infinite amounts of resources, which tend not to exist in the real world, to say it bluntly. Exponential growth may happen for a while if there are a few individuals and many resources. But when the number of individuals gets large, or large enough, resources start to get used up, slowing the growth rate. Eventually, the growth rate will plateau or level off, making an S-shaped curve, as we can see below. The population size at which it levels off, which represents the maximum population size a particular environment can support, is called the carrying capacity. And that is a very important term, carrying capacity. We can see it as an asymptote on the graph here. This curve is symmetrical and has an oblique point of inflection when y is equal to half of the carrying capacity. So if we call the carrying capacity C, and therefore this is y equals C, then here this will occur at a y-coordinate of a half C. Logistic growth is governed by the differential equation shown below. This is not on the formula sheet. dp dt is equal to rp k minus p, and that can be changed into the solution p equals kp naught over p naught plus k minus p naught e to the negative rkt. We can show this by the method of separation and integration, and we'll look at that in examples that follow. P is the population at any time t. P naught is the initial population. K is the carrying capacity. R is the intrinsic growth rate, the rate at which the population would grow if resources were plentiful. In other words, R is associated with an exponential growth rate. The above graph was released on the 16th of April 2020 by the Australian Government Department of Health. Note that the cumulative cases demonstrate logarithmic growth. At this point in time, the government had implemented strict social distancing measures to flatten the curve, to keep the cumulative cases below the carrying capacity of the country's health services. So we can see the logistic curve just here, and then we can see the actual growth. But then look what happens along here, and that's because of the measures to flatten the curve.